Have you ever wondered how astronomers look at a point in the sky and derive anything from it? How can a bunch of points of light turn into in-depth information? Well, one of their most powerful tools is something called isochrone fitting. But first, let's look how we got here. Back in the 1910s, Engineer Hertzsprung and Henry Norris Russell each independently developed what became known as the HR diagram, a plot of stars showing the relationship between luminosity and color. The higher on the diagram, the brighter, and the farther right, the redder. It's important to note here that the color of a star is directly related to its temperature, and the luminosity, or brightness, is directly related to its mass. In the 1940s, the infamous Manhattan Project made significant advances in the understanding of nuclear fusion, which led to significant advances in the understanding of stellar evolution. Finally, in the 1950s, the first isochrones were created, theoretical lines on an HR diagram that shows the evolution of many stars of the same age, only differing in mass. The basic steps to fit a star cluster goes like this. Take a bunch of stars from a cluster, then plot them onto an HR diagram. Then, plot an isochrone onto the plot. Then, we tweak the variables until it looks right. We can then be relatively confident that the star cluster lines up with the variables we selected. Now, it's time to see these steps in action. First, I downloaded some theoretical isochrones from Harvard's MIST datasets. I can take those datasets and see what they look plotted using Python or any other data science language. Now, we can start downloading the actual star data. I've chosen to use the Gaia telescope as my source of data, specifically its third and most recent data release. I pick a point in the sky towards the cluster Messier 67 and scan for data. I can then plot these onto an HR diagram. Then, finally, I can lay my isochrone on top. Tweaking my variables, I can eyeball the shape that fits best. Based on these isochrones, it seems like Messier 67 is around 5 billion years old, 800 parsecs away, and has a similar metallicity to the Sun. Now, let's see how close we were. Looks like we got pretty close on everything, so as you can see, isochrones are a pretty good way of estimating these star clusters. So congrats! You now have a basic understanding of what isochrone fitting is and how it can be used to extract information from star clusters. As isochrone fitting has gotten more powerful and more precise, the community of thousands of scientists and researchers that have all contributed to these stellar evolution models are to thank. The key to understanding the universe is communal, and stellar isochrone fitting is evidence that the universe can only be unlocked by the force of thousands of minds.